My name is John Paul Cook, and along with my collaborators Brian Katz and Milos, we're going to be talking about guided reinvention of concepts in ring theory. So here's a brief outline of our talk today. I'm going to be taking the first bullet point, which is basically to give you some context and background about the larger research program that this talk comes from. So we're going to be focusing on a very small part of that today to give you a feel for what we've been doing, for what's going on. But in this first part, I'll provide you with some of the necessary background information. And then Brian's going to take over and discuss a specific portion of the instructional sequence along with showing a specific classroom episode. Then we'll discuss and analyze that as a group and conclude with talking about future work. So this talk, the larger research project that I mentioned, is part of the special interest group of the Mathematical Association of America on research and undergraduate mathematics education. Guided reinvention and more broadly IBL is a very hot topic right now in the room community. So if anybody is interested or has had designs on attending that conference or getting more involved with room, I would really encourage you to consider attending the upcoming conference in February in Pittsburgh. So if you're interested, please feel free to ask Milos, Brian, or I. If you actually want your questions answered, though, I would direct you to John and Annie Selden, sitting right over at this table. So anyway, the primary goal of this of the research program is to develop empirically based, research-based instructional materials for guided reinvention in ring theory. So I haven't really told you what guided reinvention is. The short answer is that it's exactly what it sounds like. It's a form of IBL basically that focuses on formalizing students' informal intuitions. So you put them in a context where their informal strategies can serve as the basis for more formal mathematics. And the idea behind that is to have them feel some ownership over the material once it is formalized. So when they open a textbook and they see the definition of ring, sure, it was written by somebody else, but it's their definition. Now, I'm sure that a lot of this is resonating with what you already knew or believed about IBL. This is just a particular way that this term guided reinvention is characterized in the literature. So some examples or some examples of other research projects that are going on in the room community right now. We have groups that are studying sequential and series convergence and other topics in real analysis. So group theory, group isomorphism, quotient group, things of that nature, and span and linear independence for linear algebra. Specifically, we are going to be talking about the use of solving equations to motivate the ring axioms and some of the other important ideas in introductory ring theory. So more specifically, our instructional materials center on the idea that the ring axioms can arise as the properties needed to solve equations on various rings. So additive inverse, additive identity are usually ones that come right out of students' intuitions, and then these are gradually, the rest are incorporated, and then these are gradually transitioned into more formal mathematics. And so eventually, they start as a strategy, some informal intuition, and gradually the students begin to see them as axioms that characterize algebraic structure. So earlier phases of this project, we've tested and developed a set of instructional materials using small-scale teaching experiments, and we've been working on scaling those up to a more typical classroom size. In doing so, we're trying to answer the following very broad research questions. One, how do students come to understand ring theoretic concepts in this very specific setting of guided reinvention in an IBL setting? And two, kind of the other side of the coin there is, what can the instructor do to facilitate, support, leverage this very powerful student thinking that emerges as the process goes on? Specific to our talk today, one thing that we'd like to focus on is this construct called the shift in attention. And that's another term that's almost exactly what it sounds like. But instead of giving you the definition from the literature, I'd like to give you an example. So in a previous phase of this project, we found that students conceptualize a unit in several different ways. So they can conceptualize it as a pattern in an operation table. So for example, if you had the multiplication table for Z mod 12, the units would be those rows and columns, or would correspond to those rows and columns that might have some, the students tend to call it the Sudoku property, right? So the zero divisors will have some kind of repetitive pattern and the units won't. They can also conceptualize it as a tool for solving equations, multiplying both sides by A inverse. They can see it as a property of an element, or on an even more formal level, they can conceptualize it as a property that characterizes an algebraic structure such as a division ring or a field. So tying in with guided reinvention here, notice that these shifts all gradually get more formal. They start off with something that you can identify right off the bat just visually, and then transition or shift to more formal mathematics. And so we're interested in, well, one, what enables the students to make these shifts, to shift their attention to gradually more formal pieces of mathematics? And two, what exactly can the instructor do to facilitate these shifts in attention? So hopefully that gives you enough background. And at this point, I'm going to turn it over to Brian.
Thank you, John Paul. So we're going to eventually watch a 3.5-minute clip of my classroom, and there are sort of three things you might want to pay attention to. One would be the instructional design, how I set things up, what I'm doing and what the students are doing. And so what I'm going to do now is tell you about what I was doing so that you can focus on what I'm doing in the video and what the students are doing in the video. I'm going to knock one of those out. So my goals for the course overall, I frame the course around structure. Algebraic structure in the sense of like the content of abstract algebra, structure of proof in the sense of really understanding how quantifiers work and things like that, and the structure of inquiry, comments I said earlier, really bringing the inquiry to the surface and students feeling like they actually know what's going on, why they're asking the questions. And then some other goals, some of them affect, some of them skills, like I want the students to feel like the content was actually theirs as opposed to mine, and that they develop skills for collaboration and communication. All right. In this particular episode, so we're actually going to talk about the development of their understanding of cancellation and zero divisors. So the word doesn't come up, but integral domain is sort of in the background. That's really what's happening. I want the students to believe that this idea is natural, where this idea, in my experience, is one of the most unnatural for most students. It's the first time that they say, I'll play your game, but I have no idea why I would pay attention to elements that way in a ring. And it's a weird property where it mixes certain kinds of thinking, and if they don't start learning it now, the later ones get harder. So we'll talk about that more in a second. And that there's some charts involved, and they internalize the habits of organizing examples to actually lead to conjecture. So, just in case you don't remember, cancellation says in a ring has cancellation if for any non-zero element in that ring, ax equals ay implies x equals y, i.e. you can cancel, which you can do in groups. If you remember, you can do it in groups because everything has a left inverse in groups, and so inverses are popping up, and so those words. So this is a weird property I claimed, and so going back to the Simpson-Selikova sort of framework shifts of attention, there are some specific elements involved, ax and y, but we don't know exactly which elements, so they have to do with all elements. We'll be working with specific rings, and yet what we're really leading towards is a type of ring. And I think this property is weird because it mixes sort of a type of ring with specific elements in that ring. And I think that makes it particularly challenging through this framework. That sort of explains why it's particularly challenging. But it also explains how we built the materials to go through these 4 levels, paying attention to specific elements, kinds of elements, specific rings, and kinds of rings to lead towards this the conjecture. So the first step in the instructional sequence is happened on day 5 of this unit, where they classify all equations that form a plus x equals b and a times x equals b. All of the linear equations where a and b are any elements in these 4 rings. Real, Z5, Z12, and Z, based on the number of the solutions. So if you're looking at the handout, you can follow along. You can see these, and so the image that's on the screen is the one we did together, the real numbers. We classified solutions together, and then the students built charts, and you have images of those charts for the remaining rings. And this is about specific elements and specific rings that they're working with. Although the infinite rings, they do have to start to be a little bit more general. The next step goes to types of elements, or relationships between elements. And this was a rough phase, but the video comes after this. Develop a classification of the types of elements based on their solution behavior. And if you're not familiar, in terms of, well, the additive equations all work the same because you're in a group. But the multiplicative ones work slightly differently, and so there are 4 really interesting different kinds of elements. 0 behaves one way, units behave one way, 0 divisors behave one way, and then there are some elements that are none of those things. So those are the 4 kinds of elements, and that's the classification. And then we move to kinds of rings. So specific rings with what kinds of elements do they have. So we made a chart for each row is a ring and what kinds of elements it has, and then also whether or not we believed it had cancellation. They believed it had cancellation. And so that's about specific rings. And then we move to types of rings, which was conjecture the general pattern here. And this is the pattern, and they in fact got it right. So what you are going to see is you're going to see a video clip. The students are presenting, this is the chart from one of the 4 groups in the classroom where they talked about specific rings, what kinds of elements, and whether or not they had a cancellation. You're going to hear part of the presentation, the general part of the presentation, in which they tell us about their thinking, and then it moves, and there's some confusion in there, and then it moves into their conjecture and framing that conjecture in a way that is, I thought, more likely that they would succeed if they when they needed to prove it. So now it is Milos' turn.
While you are watching this video, I'd like you to pay attention to 2 ideas. One, what shifts of attention are happening with the students? And 2, how is the instructor facilitating those shifts of attention?
We also generalized Zn when n was prime and when n was not prime. When n is prime, we know that it's a group ring, so it follows the same steps that the group ring did. Then when n is not prime, when n is not prime, we know that we have 0. We know that the units, we have 1, but then all the other units are every time that the element is not a multiple of a factor of n. This is really wordy. We couldn't
Relatively prime. The phrase is relatively prime.
Which is what that means. Fill that in down there. And so then all the other elements that are a factor or a multiple of the factor fall under 0 divisors. And then we know that there are no others and that cancellation law doesn't work because Z12 is a good example of that. And then
So Z12 doesn't work in Z12. Do you think for any non-prime there will be a problem?
Yes.
So I'm thinking of a non-prime number. Can you give me a multiple? So what you're producing here for cancellation is AX equals AY, but X does not equal Y, right? Okay, so I'm thinking of a non-prime integer.
Okay. Me too.
Well, we're thinking of all non-prime integers. Can you give a specific? So what does it mean not to be prime?
It means
Factors. Okay. So how are you going to use? So which one of these things is going to be the factor?
the opposite. No, sorry. The A.
Okay. So let's let A be a non-trivial factor. Then what's your multiple solution here?
One of them is 0, and one of them is the other factor.
If X is its complement, are these two equal? But X is also not 0? Great. So this shows that having 0 divisors is a version of cancellation failing. Right? So it's not. Okay. So what is your conjecture then?
Our conjecture was let R be a ring. Cancellation works if and only if no elements in R are 0 divisors.
Okay. So we could define. We might want to define a ring. So how would you define a cancellation ring? What's the natural definition of a cancellation ring?
prepping for which cancellation levels.
Lovely. Does everyone like that?
I like that.
So you have a conjecture. A ring is a cancellation ring if and only if.
The cancellation level.
No, that's the definition.
Okay.
Now the conjecture.
Oh, it works.
But that's the definition. If.
So there are no elements in R that are zero divisors?
Okay. So we have to prove this theorem.
Okay, so I would like you all to take a couple of minutes in your group and answer those two questions. Again, they were, in what shifts of attention did you notice with the students, and in what ways did the instructor facilitate or support those shifts? Okay, so let me just get one or two comments from you all. Which group would like to share? I'm excited. Okay, the group right up here, would you like to share what you noticed the instructor doing in this session? So what shifts of attention did you notice, and in what ways did the instructor support those?
Okay, so I'm Fred Butler. So we noticed the students kind of going from the specific idea of like having zero divisors in Z12, and then moving toward that as a general property of rings, and how it relates to the cancellation law. And we saw the instructor supporting it, trying to get them to move toward the more general property in rings. And also he was focusing on understanding what the difference is between the definition of I guess it was the cancellation law versus the zero divisors, and how those two things were related, and not confusing the definition with the equivalence that you were trying to prove in the theorem.
Right, right. Okay, thank you. Thank you for sharing. I know we have 0 minutes or close to that, so we're just going to conclude our presentation with saying that there are a number of ways we would hope to support the IBL community. One way is to take these notes that we've created and to revise and improve and share those materials. We are also in search of, I guess it would be not even beta, alpha testing, if somebody would like to take these notes and try them out in their own abstract algebra courses. We'd also like to develop support materials for instructors. We'd like to put that added edge because it is, well, not extremely, but quite tough for a beginning teacher or even an experienced instructor to jump into guided reinvention or IBL in general. And so we would like to include those instructor materials with specific examples of both what the classroom does and interacts, and then the student thinking. And lastly, we'd like to continue to connect IBL with the room community. So to try to get more cross-collaboration between the two.
Define that acronym for them.
What's that?
Define that acronym for them.
Oh, I'm sorry. ROOM is Research and Undergraduate Mathematics Education. And IBL is, okay.
We got that one.
Okay, so here are our references. Thank you.
Yeah. Happy to chat later if you want.
We do have time for a couple of questions. If you have them, make sure you go to the microphones and state your name.
We're ready to get here together. Hi, I'm Ann Cawley from the University of Michigan, and Brian, as he was sitting at the table, mentioned something that I had noticed in that clip, which is wait time. And so I wondered if you had any other clips that you found were more, I don't know, allowed for that, or if there's going to be access to something like that that we can take a look at.
Yeah. My students think all I do is walk around and smirk at them. And in many ways that's true. And so this is a little bit uncharacteristic, this level of that. And so we have 8 days, 75 minutes each of a lot of video. And so when they're in small groups, it happens to be the group that's presenting. We have us there, and so you can see how I interact with the small group, and then you can also see how the whole class interacts. And we chose to talk about the whole class interacting because when new practitioners imagine the classroom, I think they can imagine small group work because they could do small group work in lots of settings. But leading a class discussion that came from a student presentation is one of the things you don't have an example of. So we thought we'd show one that was not perfect. And by the way, I know that it comes across like I have no sense of humor in this video. I thought those things were funny, you couldn't tell.
You guys mentioned connecting IBL to Room. Could you clarify what you mean by that?
Yeah, so I think that in IBL, at least in my impression of IBL versus Room, and you can all correct me if I'm wrong, is that IBL is focused on teaching strategies and ways to kind of enhance the classroom. And Room is not far from that, but there are also sub-areas of Room that focus on specific student learning in certain subjects or specific student learning as a whole, which may or may not be discussed in this kind of conference. So on the other end, I think that the Room community will always be, well, not always, let's hedge our words here, will mostly be accepting of different teaching strategies. And so there could be some research areas in undergraduate mathematics education that focus on how this teaching strategy helped in the classroom. Especially, Brian set up a lot of, and I'm using a math ed term, socio-mathematical norms, which are these maybe spoken or maybe unspoken rules in the classroom dealing with mathematics throughout the whole 10 days of his teaching. And we were so impressed by that, we were going to take another look at the data and try to tease out those socio-mathematical norms so that others could try to incorporate them in the classroom.
Okay. Just one clarifying question. Are you talking about connecting maybe the Academy of Inquiry-Based Learning to Room, or just like maybe bringing up more discussions about inquiry-based learning in the Room community?
Individuals, so people who are interested in using education research methods, making sure that people who might want to consume that research are aware of them, and vice versa, like Vilma and Anne's data, people who they might want to study are accessible, and so just making bridges, but between individual people.
John Selden here. It's kind of late in the afternoon, so I'm not sure I kept up with you. So if I'm asking a question you've already answered, just tell me.
It's okay.
But I'm kind of interested. So you're pointing to a situation where a student is shifting attention from one kind of thing to another. Okay. Now, is that connected to, well, there's good times to do this and bad times to do this, or there are several ways to shift attention? In this case, there can't be but 3 or 4. And is it supposed to be that, well, if people shift their attention in some certain way at some certain time, that they're more likely to come to a reasonable conjecture or something like that? Are you trying to put this in a larger thing?
If we were to generalize in that direction, since I was there, I'm the one who basically has memorized the data set, my guess is that things that would be most interesting to other people are what of the suggestions I provided did the students use and use successfully? Kind of in the like Model 2 versus Model 4 transition. I mentioned a chart, and there were a number of charts in this phase where I sort of encouraged the students to interact, to organize their examples. And when they made this conjecture, so this is not the small group moment when they made this conjecture, but there was no work. They just said, oh, the conjecture is there are no zero divisors. And it was clear that because they'd organized and they'd taken that habit up. So what kinds of things scaffold those shifts of attention is my likely guess as to what would come out of that kind of work.
When there appears to be no work and somebody does something, usually there's some subconscious work. I conjecture.
Yeah.
Oh, yeah.
I mean, if the thing they do has any sense at all.
But that also lends, I mean, they were immersed in it for 2 whole days, 75 minutes plus whatever they did at home. So when you are prepared in a situation some conjectures might just fall out.
And you may have noticed I used the word multiple solutions in a situation where it wasn't AX equals B. So multiple solution versus zero divisor versus those terms got muddy, and that's, I think, where that work was happening, where they were realizing that these were the same idea much earlier during their specific computational work.
Yeah. Thank you, Jen.
Okay, it's actually time for break now, so let's give this last group of people a round of applause.